All right, so let's see, we're in section 7.4 now. All right, so before we start, let's figure out what we mean when we're talking about a matrix. What is a matrix? Any ideas? So in general, matrix is just some objects that are arranged in rows and columns. For what we're going to do, the objects are just going to be numbers. Or sometimes we'll have some variables. But you can put lots of things in matrices. You can have matrices of equations, you can have matrices of functions, you can have matrices of other matrices. So lots of things in matrices. So for example, I could say matrix A is this matrix that. I just made up the numbers. So that would be matrix A. We usually use capital letters for matrices. In our book, you'll usually see capital letters for matrices. Just a reminder, this way is rows. This way is columns. So row 1, row 2, row 3, column 1, column 2, column 3. The objects in the matrix are called elements. So we have matrices filled with elements. And the way we write an element is by its position in the matrix. So this is an element A sub I j. This tells which row it's in. This tells which column. So for example, A sub 3, 2. So this is, we don't put a comma or anything here, but this is, we read these separately. A sub 3, 2 in this matrix. Third row, 1, 2, 3. Second column is 8. So that's the element in the third row, second column. The order or dimension is rows by columns. So for example, A is a 3 by 3 matrix. Its order or its dimension is 3 by 3. A square matrix is n by n. So that just means rows equals columns. So we can also see, since A is 3 by 3, A is a square matrix. Square matrices are nice. They have, there are a lot of things that you can do with square matrices that you can't do with other kinds of matrices. For the most part, we'll work with square matrices. We can also have a Rho matrix is just one row. So it would be A11, A21, sorry, 1, 2, A13, dot, 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 for however many columns we have. That would be a row matrix. And a column matrix just means we have one column. So that would be a column matrix. And what we're going to do today is turn our systems of equations into matrices. And then we're going to solve our system of equations using the same operations that we did to solve our system of equations. But we'll have our equations in a matrix. So for example, today what we want is we're going to take something like 2x plus 3y minus z equals 4, x minus 2y plus 3z equals 8. I'm just making up these numbers. 3x plus z equals 5. So this is our system of equations. What we're going to do is take this and turn it into a matrix. And to do that, we just leave off the variables, the pluses, the minuses, and the equal sign. So I would make the matrix 2, 3, negative 1, 4, 1, negative 2, 3, 8, 3. When I don't have a variable there, I'm going to put a 0 in, 1, 5. And our book, and I like to do this also, we'll put a dotted line here to separate the part that's with the variables to the part that's just the numbers. This part of the matrix, if we just put brackets here, this is called the coefficient matrix. Because it's a matrix with the coefficients that are in front of our x, y's, and z's. And the entire thing with the column of constants is called the augmented matrix. Augment means to add to, so we're adding the constants to the coefficient matrix. So your book will use these terms, coefficient matrix, the augmented matrix. That's what they mean. And what we're going to do now is do our operations on this augmented matrix. And really we're doing the same thing. It's a little cleaner because you don't have the pluses and minuses and x's and y's and z's and equals. You just have the numbers. So that's why I said some people prefer to use matrices, or some not prefer, they like to use matrices because it's a little cleaner. For some people it's a little easier to see. And what we're going to do is once we get this idea of the matrix and the augmented matrix, we're going to, instead of doing the operations on the matrix, we're going to then figure out how we can treat a matrix as one thing instead of a thing that has a bunch of other things in it. So we have the matrix is one thing, And we do these operations on the matrix rather than on the things in the matrix. And we can solve our equation by doing these operations with the matrices. So that it lets us treat a system of equations as kind of one thing instead of three things with three variables. So it gives us a different way to work with systems of equations. We work with matrices as if they're one object. And that's a very, very powerful thing. And another thing that makes it nice is computers are really good at doing it. So let me write down our operations, but translate them into the language of matrices. And then we'll do one example, and then we'll be done. So our operations. They're still row operations. They're the same things that we did before. We're just using matrix language now. Our first step is we can exchange two rows. So we can switch the order of the rows in the matrix. And that doesn't change anything. We can replace a row by its multiple. So all we're saying there is we can multiply a matrix, or a row by a number, and use that for our new row. So we might want to, if we have, say, 10, 5, 20, we could divide everything by 5. So multiply by 1/5 and replace it just to make our numbers easier to work with. And then our last one is the one that we use mostly. We can replace a row by the sum of itself and a multiple of any other row. And all this is saying is we can multiply a row by a number and add it to another row and replace our row with whatever we get after we do that. That's what that's what we do to eliminate the x and eliminate the y when we do our row operations. But now, instead of thinking of eliminating a variable, we just want to get a number equal to 0. After we do this, so I'm going to say the new matrix after row operations is called row equivalent. And what that means is that matrix represents the exact same system of equations with the exact same solutions. We can do these operations. It doesn't change our solution to our equations. So we call it row equivalent. And our goal is to make our matrix look something like this. I'm going to say 2, 3, 8, 5. We want a 0 here. And we want 2 zeros here. I'm going to put a 1 there. So we want a 0 there, just like we tried to get rid of the x in our system of equations. We want a 0 in these two places, just like we wanted to get rid of the x and the y in the third equation. And then this lets us read off our solution, because this tells us that z equals 4, 4y plus 2z equals 1, 2x plus 3y plus 8z equals 5. So we can get our solution to our system. When we get our matrix in this configuration. It's called row echelon form. And the process is called Gaussian elimination. Because it's the same process we use with our system of equations. Now the book talks about it, and it mentions it in the homework. We won't have to do it. I just want to mention it so when you see the words, you have an idea what they mean. You can keep going here and get zeros above the diagonal also by doing row operations and getting ones along the diagonal. If you do that, that's called Gauss-Jordan elimination. It's a lot more work. But when you do that, you can just read off z equals 4, y equals 3, x equals 5. So the process of getting zeros above and below this diagonal is called Gauss-Jordan elimination. And when you get ones on the diagonal and zeros above and below, the matrix is in reduced echelon form. So just so you know those terms. But I won't, it's a lot more work, so I don't have us do it. All right, so questions. I just want to go through one example of translating a system into a matrix and doing the row operations, and then we'll be done. So here's our system. So there's my system of equations. I'm going to translate that into a matrix. So my matrix is 1, 2, 3, 4, 3, 7, 11, 15, negative 2, negative 2, negative 1, 0. So there's my matrix. And just like with systems of equations, I'm going to write another matrix below here. The first row doesn't change. So after our first round of row operations, we want to get rid of that 3. We want to turn that 3 into a 0. So we're going to use the first 2 rows to do that. So what do we do to those first 2 rows to get this 3 to be a 0? So we want to add or subtract these rows somehow to get rid of this 3. If it were a system of equations, what would we do? This was x plus 2y and 3x, 7y. What would we do for our first step? Multiply the top equation by negative 3 and add to the second equation. So the way we're going to write that, I'm going to write it next to the row that I'm replacing. I'm going to say negative 3, row 1, plus row 2. That's how I get this row. So I do this operation, negative 3 plus 3, I get a 0 there. Please make sure I don't make an arithmetic error. Negative 6 plus 7 is 1. Negative 9 plus 11 is 2. Negative 12 plus 15 is 3. Did I do that right? Yeah. Okay. So that's our new second row. Now I'm going to use the first row and the third row to get rid of that negative 2 in the first column of that third row. So what am I going to do for that one? Negative 2 times row 1 plus row 3. That's what I'm doing to get this new row 3. So when I do that, I get negative 2. It should be positive 2, right? Positive 2. So positive 2, so I get a 0 there. 4 minus 2 is 2. 6 minus 1 is 5. And 8 minus 0 is 8. So that's my new matrix. And now I'm going to use the second and third row to get rid of that 2, because I want these two both to be 0. So let me write my new third matrix, my row equivalent matrix. 1, 2, 3, 4, 0, 1, 2, 3. That's going to stay a 0. So how am I going to get rid of this 2? Using these two rows. Negative 2, row 2 plus row 3. So that's how I'm getting this new third row. So here I just get a 0. I get a negative 2 plus 2. I get a 0 there. I get a negative 4 plus 5 is 1. Negative 6 plus 8 is 2. And there is my matrix, my row equivalent matrix in row echelon form. And now I can translate this back. I'm going to write this step just so we see how we translate it back. Once you get here, you can solve for your x's and y's and z's straight from here, but I want to translate this back to a system of equations. So we get x plus 2y plus 3z equals 4, y plus 2z equals 3, and z equals 2. That's my new system of equations. Now I can plug this z equals 2 into the second equation and get y, and plug the y and the z into the first equation to get x, and I get my solution is 0, negative 1, 2. That would be my solution to that system of equations. What would happen if I ended up with 0, 0, 0, 0, 0, 0, 0 in that last row?
No solution.
That would be 0 equals 0. Infinite number of solutions. If I got a 0 equals 1, that would be a no solution. And if you translate it back into your system of equations, if you don't see it right away, you can always translate it back to your system of equations. So all we're doing today is going from a system of equations to a matrix, and then a matrix back to a system of equations to get our solution. And some people prefer to do the system of equations this way because it's a little cleaner, maybe a little easier to see. All right. And once I write the homework, I have an interesting historical math fact to tell you. It is not a joke. And then these two on page 501 are a couple of parabola problems. And you can do those with matrices. Number 67 in your book says to use Gauss-Jordan elimination. You do not have to use Gauss-Jordan elimination. Just do the normal Gaussian elimination. So just I wanted to point that out. All right, so there's that.